Okay, hi everyone. Welcome to this 33rd Data Science Leuven meetup. As you know, talks start at 7:30, which is now, but first a small introduction. What is the agenda for today? First up, we will have Rebecca Li and Allen Butler from Hub, who will talk about what drives future customer value, causality machine learning. Our second talk will be Mike Friedman and Jesse Blum, who will talk about the European data labor market. Where are the data jobs and what are companies looking for when hiring data scientists, data engineers, machine learning engineers, and data analysts? And then our last talk will be Luca, who is from Italy, Pisa, the St. Anna School of Advanced Studies, and we'll talk about investigating the main drivers of honeybee colony loss through discrete optimization. So first up is Rebecca and Ellen with a talk on, and I forgot it, what drives future customer value, causality machine learning.
Yeah, can I share my screen right now?
Yeah, you can.
Okay, could you see my screen? Hello? Could you hear me? Hello?
Yes,
Hey,
Rebecca?
yeah, could you hear me?
Yeah, you're good to go.
Okay, good. So, hey, good afternoon, everyone. This is Rebecca, and today Alan and I will present the topic causal inference with an application of identifying drivers to future customer value. So, we are from HEB, a grocery company, customer marketing AI team, and very glad to meet all of you here today. And let me have a quick introduction why causal inferences is very important to HEB. So HEB is a Texas-based army retailer in the United States. In order to keep HEB competitive, one of our missions is to deliver great customer experience consistently and drive customer loyalty. Currently, HEB provides a bunch of offerings in the assortment covering national brands, private labels, food as wellness, etc. With the expansion of the mixed offerings, it is very important for us to identify the incremental effect for each offer so that we can provide insights to optimize future best offers. So in this meetup, we will focus on an application of model ML causal method and its comparison to econometrics approach. Before jumping to the methods and application, I would like to walk through what and why of causal inference first. Causal inference, also called causal analysis, which aims at studying the cause and effect relationship of treatment and outcome. Specifically, it is a process of drawing a conclusion that a treatment was the cause of an outcome. And and the reason the causal inference matters a lot since it bridges the gap between prediction and decision making. Currently, we can predict customer future value from modelings, right? But that doesn't help business understand what is really causing that. If business want to drive more future customer value, they cannot make decisions based on the prediction, but could base on the explanation what caused the incremental customer value. Therefore, causal inference creates the interpretability and transparency to stakeholders. That's the reason we want to work on the causal inference. Another concept I would like to call out is correlation. I believe everyone here knows correlation doesn't imply causation, and I still would like to use HEB customer purchasing behavior as an example to walk through it. So at HEB, we noticed that on-brand product customers are spending more at HEB compared to the customers who didn't purchase on-brand products, which means that on-brand customers are more strongly correlated with overall spending. However, we cannot draw the conclusion that on-brand products drive future customer value. The reason is that there is a common cause which called customer loyalty that can impact both on-brand product purchase preference and overall spending. Specifically, a loyal customer will tend to both purchase on-brand products and spend more. So in fact, the total association between the on-brand product and the overall spending is a combination of causal association and confounding association. The causal inference will separate the causal association from the total association, which is the object we are interested in. Okay, I will turn it over to my team member, Alan.
Thank you, Rebecca. So our specific problem arises because past purchases are not in a pre-designed treatment. We have a panel data problem and a longitudinal multi-level problem where we want to identify three things. And that is the velocity of past own brand product purchases to future amount, the velocity between purchasers and non-purchasers, and also the incremental effects between purchasers and non-purchasers. So to identify drivers to future customer value, we use two methods. The econometrics approach using fixed effects, and also using a new development in machine learning called Causal ML. We then present and contrast these results. Businesses not only care about what is going to happen in the future, but they also want to control for things we cannot see. We care about these causal relationships when we want to make important business decisions. For example, what is the future incremental value of an own brand product on customer spend? Doing this, we cannot just compare one customer who purchased a product versus another due to confounding variables, or variables that are both correlated to our variable of interest, own brand product, and correlated to our outcome variable, future sales. So how does fixed effects work? Fixed effects helps us measure the causal effect and avoid omitted variable bias by using time to mean data and an entity to mean OLS. For each variable of interest, we capture all time variant factors, such as various basket statistics. That means for each variable of interest, we subtract each observation by its entity mean to take out those unobservable entity unique but time invariant variables impacted from our outcome variable. By doing this, the unobservables that are constant across time are wiped out. Next slide, Rebecca. Yeah, thank you. So for the fixed effects assumes that the causal effect is constant or doesn't change over time. This has some pluses and minuses. One downside is that this fails if we have reverse causality. For example, it's not the product that's causing you to spend more, but spending more that increases your chances of purchasing that product. On the other side, if you have confounders that change in time, the panel data is a very useful leverage for fixed effects to explore. So let's look at an example of our results. Although we cannot control for the own brand product sales and other attributes directly, we can control for the individual itself. The data has a timeline of 3 years and is broken into 4 periods a year. In our panel data, the customer is our entity effect and our time variable is the period. The time effects control for omitted variables that vary over time for all customers. For example, own brand product sales are common for customers but vary over time. Our Y is a future-looking revenue outcome per customer. Our fixed effects model runs within each customer, and the slope on product can be interpreted as the effect of a change in the sale within fiscal quarter. So our actual regression output is almost meaningless on its own. So to determine our own brand causality, we examine the relation between variance of product spend per customer and its future value. We then multiply the demean own brand coefficient by average intile demean own brand sales. Our chart is the average demean own brand product of interest sales segmented into the top 5 intile groups. By doing this, we're able to project out the incremental value of own brand product spend using fixed effects for the period or year of interest. I'll now turn the time back over to Rebecca so she can cover causal ML.
Thank you, Alan. So we will jump to the causal ML. So what is causal ML? In fact, causal ML are machine learning-based causal inference models, which starts with the causal identification and causal graph. So below is a typical causal graph, which includes arrows and a set of variables. So the arrowhead reflects the direction of causation, and variables include treatment, outcome, and covariance. Still use HEB on-brand product purchasing behavior as an example. We want to study the cost effect of on-brand product sales on future customer values. Then the treatment is the on-brand product sales, and the outcome is the future overall spending. And covariance are the financial metrics such as the sales, trips, items, etc. So in our case, the causal identification is easy since the treatment on-brand product sales happened in the past and the outcome future customer value happened in the future. So the causal identification is easy part and we don't need to spend too much time on working that. And the fundamental problem of causal inference is counterfactual. Below is an example of single binary treatment situation. In this case, we want to evaluate the cost effect of purchasing on-brand product on future customer value. So there is an example. For an individual, there are two potential treatments, purchasing on-brand products or not, purchasing or not. Correspondingly, there are two potential outcomes. Two potential outcomes. We can only observe the outcome that happen in the factual world, and the other potential outcome that cannot be observed is happening in the counterfactual world. And we are interested in the delta between these two potential outcomes, which is the individual treatment effect. And also we can get the treatment effect on the population level by averaging individual treatment effect, which calls the average treatment effect. However, in the real world, the most interesting real-life studies involve continuous treatment. At HEB, so this slide tells us how the continuous treatments work. At HEB, even we know purchasing on-brand product could drive future customer value, but we are more interested in estimating the cost effect of amount spent on-brand product. With human intuition, we guess $5 spent or $20 spent on-brand products could drive different customer values. That's the reason we will use an application with continuous treatment later. And then we can do the estimation of the treatment effect. Currently, there are some open source packages for estimating treatment effects. Here, we are introducing a package called Econ ML, which aims to estimating causal effects with ML methodologies. So in Python, we import this function, causal forest DML, from the Econ ML package to do the causal analysis. So this function, causal forest DML, is developed by Microsoft 3 years ago, and it is a combination of two different algorithms, causal forest and double machine learning. Let me give a brief summary of these two methods. Okay, start with the causal forest. So in fact, causal forest is an extension of random forest. You can see they have some similarities. Both of them are built from trees, and specifically causal forest is built from causal trees. And the big differences between random forest and causal forest is the criteria to split the trees. Instead of minimizing MSE in random forest, the rule to split causal trees is to maximize the differences across groups in ATE, which is the average treatment effect. And the second method is DML, double machine learning. So based on this causal graph, we could know that both of the covariance and the treatment will impact the output, which is the customer future value. If we want to model the outcome y out of x and t directly, we can do it, but the estimated effect coming from out of that for the treatment will be biased because covariance X also impact T. So we have to debias it. We have to take away effect coming from the X, and DML can help us do it. So how to remove the confounding effect of covariance on treatment? Here is a standard process of DML, so I will not go through this. And if you are interested in, we can look at some math formulas later together. Okay. And then let's walk through an application of causal ML at HEB. So in this case, we will use a continuous treatment. So we want to evaluate the cost effect of HEB on-brand products purchase amount on future customer value, which means we want to know the amount spent on on-brand product could drive how much incremental sales in the future. So this slide is about feature engineering. So on the right part, we could know the outcome is the spend over the next quarter, which is quarter 2. And the treatment and covariance are reflected in the left part in the quarter 1. The treatment is the amount spent on on-brand product in quarter 1. And the covariance, in our case, are the financial metrics and RFM metrics. So the RFM metrics are recency, frequency, and mandatory. Okay. And the chart on the right is the output of our causal analysis, which displayed individual treatment effect, customer ID, and the quarter, which is the period of future incremental customer value we estimated. In our data set, we are observing the customer over 7 quarters. Therefore, we will have 7 different observation points for each customer. Each observation is for each customer and each quarter. And another thing I want to call out, these numbers are fake, not the real HEB analysis result. So, and how to interpret the individual treatment effect? We can take the first row as an example. So the first row tells us for this customer, he could generate additional $20.9 in 2020 Q2 if the customer spent a certain amount on on-brand products in the prior quarter. So this is on the each record, each individual level treatment effect. After looking at the treatment effect on individual level, we would like to look deeper to see each subgroup's treatment effect. So based on the historical sales on on-brand products, we segment the customers into 20 groups here. You can see the group 20 spend most at on-brand products, and the group 1 spent at least at on-brand products. So the top chart shows the aggregated on-brand product sales in each group, and there is each group's threshold. So if a customer spends more than $20.2 on on-brand product in a quarter, then the customer will belong to the group 20. And the second table tells us the treatment effect on subgroup level, which is KATE, conditional average treatment effect. In our case, the KATE in this table is the average treatment effect on the conditions of each customer group and each quarter. So we can still use this number as an example to interpret. So the KATE value is 18.8 here, which is marked in green. It means a customer could generate additional $18.8 in 2021 Q3 if the customer belong to the group 20, which means if the customer spent more than $20.2 on on-brand products in the prior quarter. Okay. And based on the customer segmentation, and based on the threshold for each group, we think the group 20 is the on-brand cohort group. And then we can focus on the group 20 to get some conclusions. And so also if we just focus on the group 20, we can get the kit for group 20 for each period, right? So because we want to do the prediction, we just pick the quarters in the 2021. You can pick whatever period you want. We just pick the 2021 quarters here. And by doing the average, we can get the predicted quarterly kit for group 20. It is 18.5. Therefore, we could draw the conclusion that a customer would generate additional $18.5 in 2021 Q4 if the customer spent at least $20.2 on on-brand products in the prior quarter, which means that 2021 Q4 future customer value driven by on-brand products is $18.5. And the 2020 Q4 total future customer value driven by on-brand products will be $925,000. So that is additional dollars will be generated for this group because they purchase on-brand products. That's our final conclusions based on the causal analysis. Okay, and in our presentation, we introduced two approaches for causal analysis, Causal ML and a statistical approach fixed effect model. And we will deliver the results from Causal ML to stakeholders. Although Causal ML is a complex approach and it is hard to explain, but it does have huge advantages compared to fixed effect models. So first of all, it is more accurate because this approach is better at dealing with high-dimensional dataset. And secondly, it needs less assumptions compared to fixed effect models. In fact, one of the big assumption of fixed effect model is that the unobserved variables will be consistent over time, which is hardly true. And last but not least, the advantage of Causal ML is the estimator is unbiased, which is very important in the estimation part. Cool, and that's our presentation. Any questions?
Thanks for your talk, Rebecca. We're still waiting for other people, for other questions in the comments on the YouTube stream, but there is already one coming from Julien. Do you only segment the customers based on minimum sales or also on other features?
So right now we just did it on the sales because the treatment we use the customer on-brand product sales to do the analysis. Yeah, we only use the sales right now.
Yeah, because we're projecting out that future sales. That's really what the business goal is. So.
Okay. Istvan, you also had a question, I think.
Yes, yes, I also have a question. So first and foremost, thanks for a very interesting presentation. I mean, this is causality is very important, especially in market research. Now, I will admit that I did not understand all of the details that you mentioned, especially those on effect sizes, and I have a question on that. So what I know from other, let's say, causal analyses is that very often the causal effect is smaller than a non-causal effect. And in market research, we already sometimes suffer from small non-causal effects, so therefore even smaller causal effects. So isn't that a problem? Are your let's say stakeholders happy with the effect sizes that you can show with your analysis?
So first of all, yes. So first of all, this analysis results they are from the fake numbers. We generate the data randomly, software. Mm-hmm. Yeah. So this is now this number is now the real number. So so based on what we deliver to our stakeholders, and they think that's great, and also because actually we focus on some products with HEB private labels. So far, so the results from the causal ML and fixed effect models, they are not very close, but at least the result from causal ML, we think that is reasonable and makes sense.
Okay, thank you.
Just to add to that, I think that's an advantage of also breaking the customers into different groups by entiles, because you're right that the effect size is smaller for certain different segments of customers.
Thank you.
Okay, I'm not seeing any other questions in the comments. So I guess this can then conclude your talk, Rebecca and Ellen. Thanks again, also for joining from the US, by the way.
Thank you.
Thank you.
Then, it's up to our second speakers, Mike and Jesse, who will talk about the European data labor market. Mike, Jesse, floor is yours.
Excellent. Well, thank you, Sarah, and good evening to everybody. The title of our talk this evening is The European Data Labor Market. Where are the data jobs, and what skills do companies want in data scientists, data engineers, machine learning engineers, and data analysts? And just a really quick disclaimer before we begin this evening. So this is a project that Jesse and I did in our spare time, and so we are not representing our respective employers tonight. Okay, well, let's get into it then. Let's see, can we advance? Oh yeah, there you go. Right, so labor markets, it's a really big topic. We're not going to talk about everything, of course. And specifically, tonight's talk is not necessarily how to get a data job. Rather, it's about what we can understand about where the data activities are taking place based on job ads, right? So typically what would happen, I'm assuming you can see my mouse, is that, you have HR and the data organization decide, okay, well, we need to hire a data professional, and they put out a job description to the labor market here. And we just took some Google image searches for data engineers and data scientists, and this pretty much looks like what we do. And so we're trying to sort of analyze this bit here, the bit that companies push out to the labor market to understand what companies are looking for. And so, this project came about when I personally was thinking about looking for a new job. And when I was looking at job ads, I saw some strange things. They seemed to be a lot about like long lists of technologies combined in sometimes surprising ways. Like we saw things say, we need somebody who knows both Tableau and TensorFlow. And I kept thinking to myself, what exactly are companies looking for when they're trying to hire data professionals? And, we are certainly not alone in this type of reflection, thinking about, what are the different roles and how do they relate to one another? So you can see on the left a previous example of somebody who's thought about these different roles. We see the data analysts, data scientists, data engineers, analytics engineers. And it's somewhat comforting to know that at the end of the day, it all ends up in a JIRA ticket. So that's what other people have done. Tonight, we're going to be doing something a little bit different. Specifically, we have 3 goals, right? To look at the job ads and try to understand the relative demand for the different profiles. So data analysts, scientists, engineers, and machine learning engineers. Also to understand a little bit within a European scope, where are the jobs, in what cities, in what sectors? And then finally, to take a little bit of a look at the skills that employers are looking for when hiring across these roles, and how they might be similar or different across the different job descriptions, right? But before we get into all of that, let's spend just a minute talking about the data.
Right. So we needed data. There aren't the data sets just out there, so we had to do some scraping, went to the job boards and set up routines to get the data and then filter it and aggregate it and what have you. By the end of December, we had 6,500. They span. We zeroed in on these 4 different roles: so data scientists, data engineers, data analysts, and machine learning engineers. We looked at different countries, and within those different countries, we looked at different the big cities for them. And we were looking specifically at the roles, the locations, the sectors, the company size, the requested skills, and then we grabbed the job text as well and have started to analyze it.
Indeed. And so the first question that we had was, what's the demand for the different profiles, right? And so here you can see a breakdown of the number of jobs across the different roles. And data scientists had the most openings, but followed very closely, in fact, by data engineer and data analyst. It really looks like in the European countries that we were taking a look at, machine learning engineer is kind of a niche role or a niche profile. And one of the most interesting things, or the things that surprised, I suppose, Jesse and myself, was the relatively strong demand for data analysts. And especially, all the hype around data science, who gets talked about? It's the data scientists and the engineers, the ML engineers. But it's interesting to see that the demand for the data analysts is, basically just as high as that for data scientists and for data engineers. And so this, is a summary of just the numbers of jobs across all of the locations, right? So what we did next is to break out sort of the top cities for these different roles. Essentially, where are the hotspots?
So unsurprisingly, really, London, Paris, and Berlin, big capital cities, and they have lots of the jobs. In a few slides, you'll see how the different roles break down across the cities, but this is the macro perspective. One thing to note is that remote work was indicated as a separate location. And in Europe, it seems that there isn't as much remote work advertised. Now, we did this during COVID, so that's probably what you're seeing there is probably even on the high side. As if and when we ever normalize, it may go down from there. We have a conjecture that it's probably due to complex labor laws in the EU.
Yeah, indeed. Like, I was working in human resources at the beginning of the COVID pandemic, and that was a really big discussion, right? People are employed in one country and living in another one, and the tax laws, in fact, make that quite difficult. And so there was some exceptions made during the beginning of the COVID crisis, but those are starting to expire. And so for all these sort of complicated reasons, remote work across country boundaries is somewhat complicated within Europe. And so we've looked at the popularity of the roles and of the cities. And as Jesse said, the next logical step is to combine them and see, okay, well, is there the same demand profile for the different roles across the different cities? And so that's what we see on the next slide. And here we're looking at the top 7 cities, and we can see the numbers of different openings for the different roles. And it's interesting, right? So you can see that London and Dublin have a similar profile in that there are more openings for data scientists and for data analysts as opposed to data engineers. So the same for London and for Dublin. For Paris and Berlin, it looks a little bit different. They seem to have more openings for data engineers as opposed to the analysts and the scientists. And Berlin in particular stands out for having a relatively high level of machine learning engineers, right? So it's the same level as the scientists and the analysts. And so what we've seen now is a little bit about the roles, a little bit where they're located, and the demand profiles of the different cities. We'd like to shift away from this for a moment to talk about the different types of companies that are looking for data talent right now.
And just before though, there's a couple questions. So one of the questions is our data based on the job title or the content of the role? It was the job ad itself. So we took the title in, of course, but also the body of the content of the role.
Yeah, maybe just a little bit of detail. So like the way these roles were organized on the website, there was like a canonical job title that's done. We're getting into the details of how they store their data. But yeah, based in the scraping, this was the role that was assigned by the job posting site. So they do have like a fixed set of roles that people can choose from. And so we're pretty confident in the classification of the roles. Yeah, it's a little bit in the weeds, but it's a good question.
Yeah, and the other question there is, did we segment by seniority level? No, we didn't. That's a very good idea. We plan to continue to do similar analysis. So I think in the future we would do that. I think that's an interesting
definitely
perspective.
Definitely. Okay, well let's move on then. Yeah, like what types of companies are hiring? That's the next bit.
Right, so here we can see that at the top, the largest bars are business services and information technology. Unsurprising that IT is present, of course. Then you have finance, manufacturing, retail, etc. Business services, what does that mean? Well, that's basically the consulting companies. So Deloitte and Accenture, etc. There are other consulting companies out there as well. Please do your own research. But it also includes the recruiting agencies who are probably recruiting for the consulting companies, or at least for doing external placements into the other sectors. So it's a little bit of a misnomer to have business services, because obviously those people would be going into the other sectors too. Information technology is going to be well, I can't call them FANG anymore because there's like Meta and there's Alphabet. So yeah. I don't know what to call them. Again, do your own research. There are other incredibly large technology companies out there. But in addition, then you have the banks, the insurance companies, the biosector, etc. There's even a little bit of media.
So. Yeah. Indeed. Well, so this is sort of one way to think about what types of companies are hiring by the sector. The next thing that we'll take a look at is the size of the company. And by size of the company, we mean number of employees or headcount. And it's interesting, actually. There's like sort of two main groupings here where you see the most roles. So the first is the relatively small companies, right, from 1 to 500 employees. And then the second one is the really big companies, so 10,000 or more employees. And so it's interesting, right? The data stuff seems to be happening in the small organizations on the one hand, and also in the very large organizations on the other. If we look and see, okay, well, what are the small companies? We see a mix of sort of specialty consultancy firms and tech startups. That's a lot of them, of course, not all. And in the large companies, you see, the large organizations, banks, insurance companies. There's some government agencies in there, state-run postal services that we all know and love across Europe, pharma, chemical, other major retailers. And it's interesting, right, to see that it's these sort of at the extremes of the headcount that you really see more demand. On the one hand, the smaller companies, they might be data focused from the very beginning, or they might be a little bit smaller, and so it's easier to integrate data activities into what they do. On the other hand, you have the larger companies that probably have a lot of data. So that's useful, and they also probably potentially have a budget to get started with data type activities. And so embedded in the job descriptions were English keywords describing requested skills. So essentially what happens, companies want to post a job ad and they go to the site and they can pick, hey, what skills are relevant, are sought after for this particular role. And so there's like a predetermined list, and that's what we're going to be talking about next.
Right. So we're talking about data scientists, data engineers, machine learning engineers, data analysts, and unsurprisingly, we find Python and SQL at the top. Other languages are interspersed about. And a lot of technical capacity, so cloud computing technologies, statistical software, and big data processing software, visualization tools. Those are the main skills. But in addition, on the soft skills side of things, we have communication, as in basically language. So if you're in Berlin, they're looking for German. Here in Belgium, they're looking for Dutch and French, etc. And that's about it for the soft skills, which I think we have some commentary on in a little bit.
Yeah.
But yeah, Python and SQL.
Indeed. Well, and from one perspective, this is like a somewhat simple way of looking at it, right? Because we're collapsing across all of the roles and sort of displaying the data, just for everybody all combined. But we were actually quite curious as to see, how the roles differ from one another based on the skills that are expected. And so that's what we'll be talking about next. So this is a cluster map that does a simultaneous clustering of both the roles and the skills. And so the way it works, you can see the color here represents sort of the relative proportion across the roles of the different skills. So the colors that are lighter indicate a higher presence of that skill as compared to the other ones, whereas the darker colors suggest like less demand for that skill in that role compared to the others. And so what do we see? Well, the data analysts, they're expected to know about the Office suite, business intelligence, marketing topics. It's interesting. You do see communication and presentation skills listed here. So we're getting a sense that, the data analysts, for example, are client-facing. Like they have to talk to the business or, to people outside of the more data technical sort of places in the organization. If you look at data scientists, what do we see? Well, a lot of statistics. There's R, there's SAS, there's MATLAB, data mining, leadership. But what's really interesting, in fact, is that there are relatively few skills that seem to be very unique to this role. And if you think about, 5 years ago, people were talking a lot less about data engineers, machine learning engineers, and we think that, data scientists were expected to maybe do a lot of different stuff in here. But at the moment, because there's these other roles, it seems to be unclear what really the specialist skills of data scientists are beyond statistics. And actually, the presentation from HEB was nice in that regard because it does sort of rely on a lot of like classical econometric techniques, mixed, of course, with machine learning stuff as well.
There's a question from Istvan asking where SAS is. SAS is there.
There's SAS.
We see it next, a little close to R. I'm not sure if you see the mouse. But.
Yeah. Oh, yeah. Yeah. So it's in between data analyst and data scientist. Yeah. As far as the data engineers, they have a wide palette of skills that are expected. A lot of technologies, in fact, big data, databases, cloud stuff. And for the ML engineers, what do we see? Software development, C, natural language processing, and TensorFlow. So they get their specialties. Definitely some software stuff in there, deep learning, NLP. And so this is like the predetermined list of skills. We talked a little bit about where that comes from. The companies choose them from a list. And so you say, okay, well, maybe the text of the job ads, which is, richer but less structured, tells a different story. And so that's what we're showing here on the next slide.
So this is a word cloud. It's grouped by color. So in the top left-hand quadrant, we see the data engineers in orange, then data analysts in the top right in green. There's very little in blue, and that's for the data scientists in the bottom left-hand quadrant, and the bottom right-hand quadrant is in red for the ML engineers. And it matches up pretty well with the heat map. Again, data scientists really are squeezed. Statistics, mathematics, prediction being their bag. Probably, again, like Mike said, 10 years ago, certainly 5 years ago, there wasn't really the data engineer role as such being advertised. So a lot of what you used to see in data scientists has migrated up there. Data analysts, Excel, dashboarding, etc. ML engineers, they have their TensorFlow and PyTorch, and they get the machine learning, not the data scientists.
Yeah, it's interesting. Computer vision is something else that comes out that we didn't necessarily see in the skills. And I also think, just to complement what Jesse said, it's interesting to see that the data analysts, well, we see stakeholders, interaction, we see insights, right? So again, we get the sense, if anybody has to talk to the business among the different roles, it might be the data analysts, at least according to the job descriptions, right? So we've gotten a sense of what the employers are expecting from the data professionals, both overall and for each role. But what are the things that we don't see here that might be important? And so this is just our personal opinion based on our experience, right? But one thing that's really important in our view is empathy, for example. And why? Quite simply because it's hard to deliver a good data solution if you don't understand your stakeholders. And there's this really great quote from the pragmatic programmer that I really like. It goes, our job is to help people understand what they want. And if you think about, data stuff is all relatively new. All of the things that we're doing, it's new for a lot of people within the organization. And so it's not the case that the stakeholders have done 100 different data projects already, right? So having that empathy, being able to understand what your stakeholders want, and then being able to sort of develop and deliver that is really important. So empathy is sort of the key, if you like, to bridge the gap between the business and the data people. Communication skills, also very, very important. As we said, all this data stuff is relatively new. And so being able to explain in plain language to key stakeholders, that could be executives, it could be other technical people, anywhere really across the business, explaining what you do and why it's important is really critical. Also, because we do occupy sort of technical roles, advocating across different stakeholders for a sensible technical approach can be very important. And then finally, communicating across data roles is also super important, right? Because we all occupy the same general space and we need to work together. And so being able to express ourselves clearly between data scientists, engineers, analysts, etc., is important. And we were somehow encouraged by the fact that communication skills is listed in 600 job descriptions. So that's already pretty good. That's just about 10%. However, the road is long because that's only 1/5 of the number of requests for Python. So we're getting there, but we're not quite there yet.
So in summary, we have looked at we collected and analyzed 6 months worth of job data across European cities and countries. We found that right now there's fairly even pegging for data scientists, data engineers, and data analysts. ML engineers are this up and coming role and that's seen in the demand. For the cities, London and Dublin have a clear perspective on data scientists and data analysts, whereas Paris and Berlin are more data engineering. Skills, Python, I'd say SQL is there.
Yeah.
One of the skills that's missing, command line, terminal, bash scripting, that kind of thing, that'll never go out of fashion, even if the HR people don't put it on their skill list. So include that in your repertoire, and probably version control, Git would be a good one as well. But yeah, the skills are hyper focused on very, very specific tools, and perhaps what's missing is empathy, communication, well-rounded individuals, some notions about governance, about project management, about requirements gathering, and your various different aspects of non-functionals, performance analysis, etc. So if you are interested in the data set and possibly doing this type of analysis yourself, that URL there goes to Mike's GitHub page, where you can explore all of the information and submit pull requests, and we can keep this thing going.
Yeah, no, indeed. Well, so to get really specific, the link goes to sort of a short essay that we wrote based on this, and that links to the GitHub. All of our data is there. Feel free to go ahead and use it to do whatever you like. If there's other things that you would like to take a look at, let us know. Feel free to go ahead and talk about it online. That's totally cool. We're big believers in open data. So there you go. That is our talk. There's questions, I guess?
Yes, there are already some questions in the chat, but there might still come in from people who waited till the end. But there's one from Andreas de Lilla, who asked, did you also look at relative size of the job openings, for example, versus the number of inhabitants? And I guess it's also related to the next question, that's from Tom Klaas. Wouldn't it be interested to also incorporate relative frequencies, as now some findings are correlated to the size of the cities/countries?
Yeah, I think the relative frequencies and also how the frequencies change over time. I think both of those will be interesting future work for us. But no, we haven't specifically analyzed them.
No, I think that's actually a really good suggestion. It's quite nice. I mean, on the one hand, that's kind of useful for giving perspectives. On the other hand, if you're looking for a job and are mobile, like maybe you don't care how many people live in the city if you want to move there. But I think both perspectives are valuable. So that's good. Thank you.
Yeah. Another question from David Kleisters. Did you analyze demand for freelancers versus employee contracts?
Yeah, no, that's an excellent question. So our data are kind of mixed. I think we did a selection for sort of permanent roles. So these aren't necessarily like freelance roles. Although when you look at, if you want to go take a look at the data, you're welcome to do that. Some of the recruitment agencies just sort of put all kinds of stuff in there. So even if you do a select on the website, give me permanent roles, sometimes you'll get recruiters putting in some freelance roles, but for the most part, it's permanent roles. Yeah.
Okay, and then there's Taufik Burgana, who says, thanks guys, how did you manage to get these data?
Yes, so we put together a scraping program that we ran every couple of weeks. And so what it did was it went to a job board and sort of, we were focused on different countries. So it went and looked for all of the jobs with the different, for each role in a given country, and we sort of pulled them down, and then there was a whole bunch of work to be done in retrieving the information from the HTML. But if you go look at the data on GitHub, we've cleaned it all up for you, so you don't have to go through that process. But that was the basic way that it happened, yeah.
And then Super Agafia is wondering if there is also some bias towards certain industries by country. I have an impression that in Belgium, the majority of data science positions are in biotech.
Yeah, no, definitely. I mean, so we actually have, let's see if we can go forward. We have some information, backup slides. Oh yeah, so we have some information on Belgium specifically. So prepared a slide. This is the intro to Belgium for all the people who are not from Belgium. Every one of these is very typical. Yeah, this is, indeed. So who's hiring in Belgium? And so, yeah, it's clearly, you know, there's different sectors in different countries. If we look at the sizes of the companies, it's in Belgium, it's more the small ones. So there's recruiters, our homegrown tech people, ML6 or X AI AppTweak, if there's anybody here on the call, awesome. Then like there's the medium-sized companies here, 1,000 to 500. And who do you see there? I mean, these are all familiar institutions to anybody who's, you know, in the market in Belgium. Telecom, Telenet, VU, public institutions, consultancy. And of course, the large companies with 10,000 or more employees, the banks, we all know about that, consultancy, pharma, recruiters. So I think that's an excellent point. There is bias just by the fact of, you know, what companies are operating in which places.
Okay, and then Istvan had another question.
So I was wondering, and I don't think your data allows for this, but I was just thinking about it, is what you often see is when you see a job ad and it lists all these great technologies, and then you go and talk with them, and then it turns out that they do nothing. They ask maybe for a TensorFlow expert. You go there and they'll say, oh, that's the dream we have for 5 years or so, within 5 years. But for the moment, we still work with Excel, right?
Yeah.
So it would be great to, let's say, to avoid that you're wasting time, if you could predict the probability of having such what I call vanity job ads. Now, of course, you cannot do that because you don't have that feature, I guess, for your data set. But I was wondering whether you have thought about something which we could call a buzzword index. So if there's just too many buzzwords, you know this is no good. Is that something that you can relate to?
For sure. Where this actually grew out of our initial thoughts, and maybe where we'll end up with in the end, is a maturity model of the hiring ads. What Mike said at the beginning, where like people will be asking for Tableau and TensorFlow, you know, a big kitchen sink worth of buzzwords and what have you. And then you look at the text descriptions, and it's fairly clear that whoever wrote that they're just open to the world. Then you get other ones which are a lot more specific, the same way that you would hire in most other industries. And certainly where we want to go with it is to be able to show that continuum and maybe help the HR companies to become a bit more specific and targeted, and so that there is a somewhat less bad feeling when you show up to the recruitment process and it's obvious that you're not the right fit, or they don't really know what they want. That it can create a lot of pressure on everybody that we would hope to alleviate over time.
Yeah, and it's just tremendously inefficient also, right? Like it scares people away who aren't able to do anything but might be able to do a job very well. And I think, really concretely, if you wanted to take a look at that, we showed the cluster analysis, right? And so what that does is it has clusters of skills. So like an idea that I had, we haven't actually done it, is like say, okay, well, for each job ad, how many different clusters appear in the job ad? And so if there's like a million different clusters of things that are super far apart from each other, well then, do they really expect all of that? So that's one way that you could do it. But it's a really good suggestion. It's something that we're thinking about.
That's right. On the upside, if a company lists SaaS as one of their technologies, they're probably actually using it. So
yeah, indeed. It's not something that, well, I can say many things. I will be quiet.
Well, you feel free though.
No, it's all good.
Thanks.
Yeah, no, thank you.
Yeah, I don't see any more questions coming in the comments, so I guess we can conclude this talk. Thanks, Mike and Jesse. I learned that I need to reconsider my job title, as I have more in common with a machine learning engineer doing NLP and testing than with a data scientist who has experience with MATLAB and R.
Well, be careful. You might not find as many jobs, right?
Also true. Okay, thanks. Next up, we have Luca, who will talk about investigating the main drivers of honeybee colony loss through discrete optimization. Luca,
Right.
the floor is yours.
Yeah. Hello, everyone, and thank you for the invitation. So, my name is Luca, and I will be talking about the main possible drivers of honeybees loss across the United States. But let me introduce myself first. So I am currently in the process of completing my PhD in data science, and my research interests lie at the intersection of statistical learning and computational statistics. I am truly fascinated by honeybees. I am a beekeeper myself as a hobbyist, of course. And here you can see some of my colonies enjoying the sun in the southern Italy. So for who's not familiar with the topic, honeybees are like a huge family. And each of these little houses that you can see in here, it contains a single queen, tens of thousands of female workers, and a very few males only during the spring season. Biologically speaking, honeybee colonies are one of the very few examples of superorganisms that we can find in nature, and they will be the focus of our analysis. Aside from my personal interest, I think honeybee colony loss is a very important topic for the whole society. And indeed, the vast majority of flowering plants necessitate of pollinators for their reproduction. The consequence is that approximately 1/3 of our food consumption directly or indirectly relies on pollinator services. And this ecological service is estimated to be $200 billion per year. Of course, pollinators do not include only honeybees, but they definitely play a major role in this picture. Unfortunately, honeybee colony loss is a widespread phenomenon, as you might have heard, and this is happening in different countries. We will be focusing on the United States, where beekeepers have suffered an average 43% colony loss between April 2019 and April 2020. And of course, some colonies have been renovated or added during the year, so this should not be considered as the absolute decrease in the colonies stock. However, looking at this plot, we can see a negative trend in the estimated number of colonies in the US between 1944 and 2008. This is due to several reasons, including stressors affecting honeybees, but also due to economic policies, business practices, and so on. Honeybee colony loss is a difficult phenomenon to study because the stressors which influence honeybee health and behavior, they are a truly complex network. So, for instance, we can see that pesticides, pathogens, or beekeeping practices, they directly affect honeybees. And indirect factors include climate and weather events, farming practices, and so on. So from this image, we can guess how difficult it is to disentangle the main drivers of honeybee colony loss. And for the US, there have been various studies which focused on one or only a very few specific stressors in isolation from others. And they typically focused on very small regions, such as single states or even counties in the US, and for limited time frames. To our knowledge, the only study investigating honeybee loss over the entire US territory and across several years was this paper of Nog from 2009. However, only land use information was used as a stressor into that model. So this was a very fast description of the problem, and I will now focus on our approach. So our goal is to study in an explorative and data-driven fashion the phenomenon of honeybee colony loss, taking into account a fairly large spatiotemporal horizon. So for instance, we will use data covering most of the US for several years. And then we also want to take into account as many possible stressors as possible, and also control variables that are useful to assess the validity of our results. And we will also rely on publicly available data. There are several problems that arise in pursuing this goal. And for instance, a single data source containing all of those information does not exist yet. And so we need to combine several data sources which have been collected by different entities and for different purposes, typically. This also implies that the data are collected at very different spatiotemporal resolutions. So we need to aggregate this data, and this requires extra care from a statistical standpoint, since we don't want to lose any information that might be in there. And such an aggregation phase would provide the so-called high-dimensional dataset, meaning that it contains several features that may be useful in describing honeybee colony loss, but we expect that only some of these are truly relevant. So here the main idea is that due to the exploratory nature of our study, we want to obtain interpretable models that can be used to guide future studies. So we are not only interested in prediction accuracy, let's say. And finally, the more variables you include into your model, and the higher is the risk that the data comes with some form of contamination. Let's say the presence of different subpopulations than the one you are interested in, or outliers. And this is more likely, of course, if you aggregate several data sources. I believe this is a very important point, and for simplicity, I will start describing the very last 2 points that you can see on this slide. So just to give you a very general idea, I won't go over any detail, but so let's consider a high-dimensional model where you have possibly even more features, which are the columns of the design matrix X, than observations, which are its rows. And since you have so many variables, it is realistic to assume that only a handful of these are truly significant, and they are enough in order to make your predictions. And let's assume now that we know the non-zero regression coefficients in beta, which are associated to the important features in X, and they are colored in black in this picture. So if this information was available, we would be very lucky because the problem would be pretty much be solved. But unfortunately, in practice, we don't have such information. And the best we can do is to fit all possible models of any given size and somehow select the most suitable one. So you can see this is kind of a combinatorial problem. And things are even more difficult in practice because these types of data often contain some form of contamination. So for instance, data recording errors or other populations. Let's say if this was a financial data set, we might have like fraudulent and non-fraudulent transaction, or if it was a biomedical study, we might have healthy and unhealthy individual. And of course, we don't have such an information available. So this is an additional combinatorial problem on top of the selection of the feature. We also want to detect and exclude the influence of outliers from the fit. And if you wonder why do we care about outliers, this is because they can hinder the performance of classical estimation techniques, such as maximum likelihood that you can see on the left, where outliers they report smaller residuals than non-outlying cases, which are these ones. And instead, if you use a robust method, you can effectively detect outlying cases, and they end up having very large residuals compared to the remaining observations. So you might say, okay, this is easy to tell, but this is the case only because we are looking at 2 dimensions. But if the problem dimension is greater than 3, we can not really diagnose this behavior through a scatter plot. So the only thing we can do is to analyze the residual of the regression after we have fitted the model, essentially. And to deal with the presence of outliers in high-dimensional settings, we rely on a robust version of best subset selection that our group has introduced in a previous work. So the idea is to evaluate all possible combinations of models encompassing a given number of observations and active variables. These kind of problems were impossible, or at least they were thought so, impossible to be solved a few decades ago, or even 1 decade ago, let's say. But nowadays, due to the advancements in hardware and optimization solvers, combinatorial problems like this one can be solved very efficiently through discrete optimization methods. It is indeed remarkable that such a non-convex formulation, where you can see the non-convexity relies on the use of the pseudo L0 norm, and also on the trimmed sum, which is over the largest residuals because they have been ordered. So it is remarkable, I was saying, that we can actually achieve the global optimum of such a difficult problem. And even if the algorithm is stopped before full convergence, we can actually certify how close we are to such a global optimum. So this is the methodology news. And for more details, you can have a look at our paper. So let's now go back to the lack of a single data source for addressing our problem. For this reason, we rely on 4 datasets which contain information at different resolutions. The first dataset is collected by the United States Department of Agriculture, and it contains information about colonies' status and stressors, and covers most of the states in the US. And it is reported on a quarterly basis for the years from 2015 up to 2019. The second dataset, this one contains weather-related information, such as maximum and minimum temperatures, as well as the precipitation level. And this dataset is provided by the PRIS climate group and is collected over a dense spatial grid of 4 by 4 kilometers, and it is reported on a daily basis. The third dataset is provided again by USDA through the cropland data layer and contains land use information based on satellite images. So this is reported over a very dense grid this time, which is 30 by 30 meters, and it's on a yearly base. And we will also use the definition of US climatic regions, which you can actually see in here. And the reason for this is twofold. So this partition allows us to reduce the number of control variables, which otherwise would be more than 40 if you use the states. And at the same time, it allows us to cluster together states which share common climatic features. And according to various studies in the literature, we also know that the presence of Varroa, which is a parasite, is something like big, let's say, that you can look with your eyes, like it stays on top of the honeybees, so it's very, very easy to detect, and it's also an important stressor for honeybees, and its effect depends on the period of the year. So in this scatter plot, we see the proportion of lost colonies for each state. So each dot is a specific state for a given quarter of some year in the US. And so we are looking at the proportion of lost colonies against the proportion of colonies affected by Varroa. And we included the least squares fit for the points belonging to each quarter of the year. So we can notice that the effects of Varroa seem stronger during the first quarter, and this is somehow known and expected. And then it's followed by the fourth, third, and second quarter. If we now decompose this pattern across different regions, we can see the top panel that colony loss usually follows a stable pattern across the years, with higher and more variable losses during the first quarter. Then the losses are lowest and less dispersed during the second quarter, and then they tend to increase again during the third and fourth quarters. And this is also in line with existing studies which link overwintering with honeybee loss. And we can also see that some climatic regions, such as West North Central, they deviate from this pattern. And I will talk a bit more about this in a minute. And similarly, on the bottom panel, we notice that also the presence of Varroa follows a specific trend, and it typically increases from the first up to the third quarter, and then it decreases in the fourth one. So a comparison of these two plots suggests a positive association between honeybee colony loss and the presence of Varroa. And here, instead, we compare colony loss trajectories belonging to states in the central climatic region, which have been smoothed into the dashed black line, against, and as also the states belonging in the west north central region that have been smoothed into the red dashed line. So you can see that these regions follow quite an opposite pattern. Indeed, colony loss peaks during the first quarter in central states, as you can see here, whereas it reaches its minimum for west and north central states. And the opposite somehow holds during the third quarter of the year. So this is just to highlight the fact that spatiotemporal information plays a major role in describing honeybee loss, and our model must take this into account somehow. So moving on to our third problem, which was about the aggregation phase for data different spatiotemporal resolution. What we did for land use was quite easy. So we followed the approach in the paper of Nog, and we computed the green area index at the state level as follows. So it's just a proportion of basically the part of land that can be exploited by honeybees over the, let's say, the urban kind of areas. And instead, for the weather-related features, we developed a more refined upscaling methodology. And this was due to the fact that weather data that were at a granular level at the resolution was much lower than honeybee data. So in order to make them comparable, we had to do this upscaling phase. And a very simple strategy might be the use of sample averages of weather indexes across space and time. But doing this, you might also incur in a loss of information. So what we did instead was to aggregate weather data based on various distributional features that are captured by various statistics, such as skewness, kurtosis, entropy, the alpha tail index, and the L2 norm. I will describe some of these later. And again, these measures are computed for each given state and quarter. As an example of our upscaling approach, this spatial statistics, they compare colony loss, which is this one, against the mean, kurtosis, and the skewness of minimum temperature. So we can see that the indexes that we built, they effectively capture different aspects of the weather distribution. In this case, it's the minimum temperature. So for instance, we noticed that the average minimum temperature separates northern with southern states, and kurtosis is higher for states in the central band of the US, which is actually the contiguous United States territory. And the skewness distinguishes western and eastern states. So now we have pretty much all the ingredients that are used in our approach. So I will briefly describe the underlying model. The response of interest, which is the honeybee colony loss, is recorded as count data. So it is likely to follow a Poisson distribution. However, instead of using a generalized linear model, we rely on a suitable transformation of this variable that can be assumed to follow a Gaussian distribution. The model at the end, of course, the error. So what we did is that for each state, quarter, and year, we compute the proportion of lost colonies and take its logit transformation. So the underlying model is now assumed to be linear, and the design matrix encompasses several types of stressors and control variables. We will also enforce into our combinatorial machinery, we will enforce the so-called group sparsity constraints, meaning that categorical features such as the region or the year, they are represented with dummy variables, and so they will be fully included or excluded from the model. And this is something which is not often straightforward with other methods. So these are the main results based on our combinatorial approach to select relevant features and detect outlying cases. So this method estimated a 10% contamination. So these results are based only on the 90% remaining non-outlying cases. And we can see that the features which have been selected include all categorical features. So we have years, climatic regions, and quarters. And we also have 11 more continuous variables. And I'm depicting with red cells factors which have a negative impact on honeybees colonies conditionally on all other features which have been selected, and the green ones on the other end, they are somehow positive effects. So I will now go into more details of our finding, and I will be very fast. So we found some evidence that the fourth quarter is the most influential one, and there's a negative impact on honeybees, and this is likely to overwintering again. Varroa destructor is one of the most harmful stressors for honeybees, and this is followed by pesticides and other factors which, this is a variable provided by the USDA, but it comprises weather, starvation, insufficient forage, and so on. And we also found that some evidence that our weather indexes can be harmful for honeybees. And in particular, we found that minimum temperature, some statistics of minimum temperature, such as the standard deviation, which is a well-known measure of variability, skewness, which is capturing the non-centrality of the distribution, and the kurtosis, which measures the heaviness of details, so how likely is to observe something extreme. And this was for minimum temperatures, and also the kurtosis of maximum temperatures was selected. So the more extreme temperatures you have, maximum temperatures, the worse is for honeybees. And also the entropy of precipitation, which essentially tells us the unpredictability of precipitation patterns. Somehow these other features were selected with an opposite sign than what we expected, but what we believe is that other pest and parasite is too strongly correlated with Varroa, so it's actually capturing beekeepers' expertise, and also the green area index, which is as a negative sign as opposed to the resulting NOG. This seems to be due to the fact that it's capturing state-level variability. So I will now conclude. I just want to mention that there are several limitations of our work, especially due to the data that are available. And we are also considering several extensions of the present study. This actually is a collaborative project. It's still going on. We will soon submit the paper. And this was a collaboration with Roberto, Stephanie, Jeffrey, Martina, and Francesca. So to conclude, I just want to remark that, to our knowledge at least, this is the first exploratory study that investigates honeybee colony loss in the United States on such a large spatiotemporal resolution, and also taking into account multiple factors at the same time. Finally, also, perhaps I should mention that a huge part of this project was devoted to the construction of the dataset, and soon our materials and methods will be publicly available for the community. So this is all I wanted to say, and thank you very much for your patience. And of course, please feel free to get in touch if you have any curiosity.
Thanks for your talk, Luca. Looking at the comments, there's no questions that came in yet, but there is a lag, so there might still be questions coming in. Or not, and everything was super clear. Istvan, you have a question.
Okay, yeah, thanks again. So last year there was, let's say, bees were in the news, so to speak, a couple of times.
Yeah.
More specifically because of the huge decline and the impact that has, let's say, overall. Can you? I did not immediately see the human factor in what you were saying, but can you link, let's say, to what extent what you described is caused by humans and which part not?
Yeah, it's very difficult to tell also because if, let's say, I will... yeah, this is, of course, we can only find associations. There's no causality near. And to see why this is a very difficult question, it's very interesting, but what you're asking is quite difficult for the methodology in use. Because you see, it's a very complex network, so we don't know whatever we found, if it's spurious or if it's an effective relationship that was found. So it should also be mentioned that we found several weather indexes that might affect honeybee health and so their survival. And of course, they might also be related to human behavior. So this is another layer of complexity, let's say, in answering your question. But yeah,
No,
this is the idea. I cannot really tell what's. Of
okay.
course, pesticides are human-made, so for sure, pesticides is something that we have found, and that is due to humans. But the other ones are very difficult to tell. You can see like precipitation, indexes of minimum or maximum temperatures. Like varroa destructor can be controlled by a beekeeper, but again, it's very difficult, especially with this data. Yeah.
I also have, if time allows, Sarah,
Yeah.
I also have a question on I saw that you mentioned the work of Peter Rousseau, so the robust statistics. So is that something that is very often used in your area of research?
Yeah, at least in mine, just because my PhD is basically on robust statistics for high-dimensional models. This
All
is
right.
like a separate work from my thesis, but this is an application of what we have been developing from a methodological perspective, let's say. And yeah, so this is not really my area. This is only an applied work that I was joining, but so I cannot really tell. I hope so, but I don't know.
Okay, thank you.
Yeah, we have one last question actually coming from Mike, I think. I'm gonna add him to stream. He can ask it himself. Yeah.
It was actually Jesse's question. Here he is.
Yeah. So I'm just wondering whether you figure the model itself would generalize outside of the American context. So could you apply it here in Europe? And if so, have you thought about getting non-American data? And would it be a ridiculous challenge to extend it globally?
Yeah. Let's see. Yeah, I think I didn't have time to mention this, but yeah, this is like the very last point. Is a future extension, and for sure it might be easier compared to the US. Like most states, at least in Europe, they are much smaller. So, for instance, I'm pretty sure that for Austria or Switzerland, maybe there have been similar studies, and the techniques are also quite similar, but we haven't tried anything yet. We don't have any of those data sets to explore yet as well. So this is a possible extension that we will try to address.
Okay, looking at the time, that was probably our last question. You do have some suggestions in the comments about using a causal inference to check the effect of human and Bayesian network approach. But then I think, thanks, Luca, for your talk. And we can start concluding this online meetup. So as you know, if you have an interesting talk, if you want to tell something on the next meetups, just reach out. We're active on social media. There's a meetup page. We have mail, or you can just contact us, one of us directly. And we hope to see you all, hopefully physically next time, on our next Data Science Leuven meetup, which will be Monday, the 13th of March. Just keep an eye out on our meetup page. It will be announced there. So see you all then. Bye.